Hello and welcome to today's lecture on audio and video compression. In the last lecture, we have discussed in detail the bandwidth and SAS factors of different multimedia signals. We have also discussed the network performance parameters of different networks. It is quite evident from our discussion of the last lecture that sending multimedia signal through internet is not possible without compression. So, in today's lecture, I shall try to give an overview of the compression techniques. Fortunately, in the last couple of decades, vigorous research in the area of compression technology has led to the emergence of sophisticated compression techniques leading to massive compression. This has made possible transmission of multimedia signal through internet. So, discussion of the compression technique is very much essential, but the subject is very vast. It is not really possible to cover everything in one lecture. A full course of 40 lectures can be taken on compression techniques. So, in this lecture, I shall essentially try to give an overview of audio and video compression. Here is the outline of the lecture. I shall give a brief introduction and then discuss the audio compression technique, particularly what is being used in MP3, that is MPEG version 3. Then I shall discuss the video compression techniques. Essentially, there are two approaches, JPEG and MPEG, and MPEG has different versions like MPEG 1, MPEG 2 and MPEG 4. I shall give an overview of these three versions, and also the H.261, which is essentially used for low bit rate compression, and I shall give an overview of that also. On completion, the student will be able to state the need for compression, why compression is needed and its benefits. They will be able to explain how audio compression in MPEG is performed. They will be able to explain the basic principles of video compression, and they will be able to explain the popular video compression standards as I have mentioned just now. Now, first let us consider the definition of compression. What do you really mean by compression? By compression, it essentially means that the compression converts an input data stream to another data stream of smaller size. So, essentially it reduces the size of the data. For example, here we apply the raw data to a device known as encoder. The device which performs the compression is known as encoder, and after this encoder performs the compression and the compressed data is sent through the network, and the compressed data is received at the other end by the decoder, which converts back the compressed data to uncompressed data. So, the need for compression is quite clear. First of all, it reduces the storage space. The amount of storage that you will require in uncompressed data is significantly larger than the compressed data. Similarly, it will require reduced bandwidth for transmission through a network. Because of lesser rate bandwidth of the converted signal, it will be possible to send through a network of smaller bandwidth or communication link of lower bandwidth. So, it will lead to lower communication cost. As you know, the higher the bandwidth of the link, more is the cost. So, lower bandwidth requirement reduces the cost of communication. Moreover, it leads to emergence of new and new applications. Some of the applications we shall discuss in the next lecture. And the compression approaches can be broadly divided into two types. First one is known as lossless compression. That means after compression, the data is reduced in size, but it is done in such a way that at the other end the original data can be recovered. So, data in original form can be recovered without loss of any information. On the other hand, there are some techniques, in fact which are more common, which are known as lossy compression. In such cases, the uncompressed data may not be exactly same as the original raw data. The reason for that is our eyes and ears do not really recognize that differences. As a consequence, we can afford to lose some information. So, even the uncompressed data in the lossy compression gives you good quality reproduction, although some information is lost. So, these are the two basic approaches we shall consider, particularly the lossy compression techniques. First, I shall focus on audio compression. Audio compression techniques can be broadly divided into two types. One is known as predictive encoding, another is known as perceptual encoding. In predictive encoding, encode essentially the differences between the samples instead of the absolute sample values are encoded. And we have already discussed in detail that differential pulse code modulation or adaptive differential pulse code modulation, where the differences between sample values are sent instead of the absolute values, and this leads to a reduction of lower bit rates. So, this is essentially the basic idea behind predictive encoding. However, the amount of compression that you can achieve by using predictive encoding is not very high. That is why the perceptual encoding is more common. It will be surprised to know that it makes use of the flaws of our auditory system based on the study of how people perceive sound. So, it essentially exploits the flaws and limitation of our ears. We do not hear everything equally. So, how it is being done we shall discuss in detail. So, it is based on the science of understanding how people perceive sound, and it is based on that the encoding is performed. We shall discuss in detail how exactly it is being done. Let us see the hearing threshold of our ears of a normal person. As you can see, this is the frequency range 0 kilohertz to 16 kilohertz, and over this range, as you can see, 2 kilohertz to 4 kilohertz is the, our ear is most sensitive to this region, and attenuation increases as we go towards lower frequency as well as you go towards higher frequency. So, you see the our ear is very insensitive to high frequencies like say 14 kilohertz or 16 kilohertz or 20 kilohertz. However, the situation is different for dogs. Dogs can hear even ultrasound, so higher frequency signal. But for human being, as you can see, the higher frequencies are not really, our ear is not really sensitive to these higher frequencies, and this is how it is expressed in decibel. So, you see 40 dB and this is 0 dB. So, our observation is ear sensitivity to sound is not uniform. So, it is not uniform, we do not hear everything equally, all the frequencies. So, audio samples that are below the threshold can be deleted. So, what is the point of sending signals with amplitude in this range of higher frequencies? In any case, the ear will not hear them. So, it is better to discard and save bandwidth of the medium of the link. That is the basic idea. This is one approach. Another is some sound can mask other sound. It has been observed that some sound can mask other sounds, and there are two types of masking. One is known as frequency masking. It has been observed that a loud sound in a frequency range can partially or fully mask another sound in the nearby frequency range. So, for example, here it is shown, if there is a loud sound in this frequency, say 8 kilohertz, then how the threshold is increased is shown by this dotted line. So, you see, if there is sound with amplitude in this range, it will not be audible to the ear. So, you can see the threshold is being raised by the presence of a signal of a loud signal of a particular frequency. So, this is known as frequency masking. Another type of masking is possible, which is known as temporal masking. In temporal masking, a loud sound can numb our ears for a short duration even after the sound has stopped. So, if there is a loud sound at a particular time instant, then some sounds around that time will not be audible to the ear. For example, whenever a train passes in the nearby region by blowing the whistle, or a plane crosses overhead, then because of the large background sound we cannot talk to each other, or if we are taking a class, it is difficult to for the teacher to make it audible to the students. So, this we have observed in our day-to-day life, and we shall see how they can be exploited to achieve compression. Here, for example, the temporal masking is explained in detail. This occurs when a strong sound A, so there is a strong sound A has occurred at time instant, say 0, of a particular frequency is preceded or followed by a weaker sound B, say suppose this is B, at the same or nearby frequency. If the time interval between the two is short, B may not be audible. For example, this signal will not be audible because it has got it is within 10 millisecond and it is about 32 dB. On the other hand, the threshold has been raised to 60 dB. You can see threshold is sharply raised, then it falls gradually. However, after 20 millisecond, it can be heard, because you can see it comes above the threshold range. So, depending on where the sound is taking place with respect to the loud sound, it may be audible or it may not be audible. So, it may a particular person may not hear, may hear, depending on when it is occurring. So, some of the signals in this range which are present can be removed from the signal for transmission. This is how compression can be done. And what is being done? The critical bands are determined according to the sound perception of the ear. So, the entire range is divided, as you can see, in 27 bands here. Of course, the range is expressed in by using a unit known as bark by the name of A.G. Barkhausen, a German scientist, and in his name it is being expressed. So, for frequencies below 500 Hertz, it is 1 bark is equal to F by 100. On the other hand, for frequencies above 500 Hertz, 1 bark is equal to 9 plus 4 by 4 log f by 1000. So, you see at higher frequencies it is more, the frequency range is more in a particular band. So, you see in band 0 it is only 0 to 50 hertz, in band 1 it is 50 to 95 hertz. On the other hand, in band 10 it is 940 to 1125 hertz, in band 19 it is 3840 to 4690. On the other hand, in band 26 15375 to 20.250 kilohertz. So, you see the range is much larger in higher bands than the lower bands, essentially because of the sensitivity of the ear is lower in higher frequency bands. This is how it is being divided. Now, let us see how MPEG-1 performs the audio compression based on the techniques that I have discussed. First of all, sampling is done at 32 kilohertz, 44.1 kilohertz or 48 kilohertz. Of course, the 44.1 kilohertz is very common for CD quality audio. Then the signal is converted from time domain to frequency domain using first Fourier transform. The resulting spectrum is divided in at most 32 frequency bands, each of which is processed separately. Processed separately means, as we have seen, each of the different frequency band are to be removed or reduced with a different way, or to be sent with different resolution. For example, frequency ranges that are to be completely masked are allocated 0 bits. Frequency ranges which are to be partially masked are allocated smaller number of bits. On the other hand, frequency ranges that are not to be masked are allocated larger number of bits. So, higher precision is allocated to ranges, frequency ranges to which our ear is more sensitive, and lower frequencies to less sensitive, and 0 bits which are not at all audible to the ear. Of course, in addition to that, in case of stereo, redundancy inherent in two highly overlapping audio sources are exploited. So, whenever we are recording stereophonic sound, two channels have lots of commonality or redundancy. So, that can be exploited or further, and that redundancy is inherent in two overlapping audio sources are exploited for further compression. And by doing MPEG-1, the audio stream is adjustable from 32 kilobits per second to 448 kilobits per second, depending on the bandwidth of the source and different frequency components present in the signal. And as you can see, whenever it is uncompressed voice, 8 kilohertz sampling frequency and a resolution of 8 bits per sample gives you 64 kilobits per second. On the other hand, whenever voice is compressed with the same sampling frequency and resolution, can lead to 4 to 32 kilobits per second. So, 8 is to 1 or 2 is to 1 compression is possible. Then for CD quality audio, if it is uncompressed, as we know, because of two channels and sampling at sampling at 44.1 kilohertz with resolution of 16 bits per sample, it gives you 1.411 megabits per second, and whenever you compress it, it gives you 64 to 192 kilobits per second. So, you see the amount of compression that is possible for audio signal. Now, let us focus on video compression. Video is essentially a temporal combination of different frames, and each frame can be considered as an image. So, image means it can be considered as a still image, and which comprising spatial combination of pixels. Now, two basic principles are used. One is known as Joint Photographic Experts Group standard, that is JPEG standard, that is primarily used to compress images by removing spatial redundancy. So, that exists in each frame. So, each frame is considered as a still picture, and spatial redundancy present in it is reduced with the help of JPEG. On the other hand, MPEG which is moving picture experts group standard, is used to compress video by removing the temporal redundancy of a set of frames, because to adjacent frames may not be maybe the differences between two adjacent frames can be very, very small. So, that is being exploited in temporal redundancy. So, these are the two techniques used. First, let us focus on JPEG. JPEG involves the following 4 distinct steps. First one is block preparation, second one is discrete cosine transform, third is quantization, fourth is compression. So, these are performed one after the other to generate the compressed output, and so raw data is received here, then block preparation, discrete cosine transform, quantization and data compression is performed to generate the output. First, let us consider the block preparation. As you know, after the video signal is digitized, it is converted into an array of pixels. For example, for CD quality or VCR quality video, this is the typical number of pixels in horizontal direction 640, in the vertical direction 480. So, you have got 640 by 480 pixels, and each of the pixel is has got RGB components, red, green and blue components. Each is represented with 8 bits. So, this leads to 24 bits per pixel. So, 24 bits per pixel. This is how the video frame is digitized, that means still image is digitized. However, before performing any compression approach, I mean before performing any operation, it is converted into luminance and chrominance component. The reason for translating RGB to luminance and chrominance is our eyes are more sensitive to luminance than chrominance. So, chrominance can be sent with lesser resolution. Secondly, this by converting to luminance and chrominance components allows more compression than if it is present in RGB. That is why the video digital signal is converted into YUV components. Of course, in each pixel has got, again in place of RGB, it has got Y, U and V components. Then and the formula that is being used for conversion is shown here. Of course, as whenever you will be playing at the other end, receiving end, the inverse compression, inverse conversion has to be done to get back the RGB. This conversion to luminance and chrominance has got another benefit. It makes it compatible with black and white technology. For example, if the luminance component is sent to a black and white receiver, we shall get that black and white picture corresponding to a color picture. Now, let us see how the block preparation is done. Each pixel is represented by YUV, and it is divided into 8 by 8 pixels. In each block, it has got 8 by 8 pixel, and each block is processed separately so that the computation required for compression is minimized. That is the basic objective of this block preparation. So, the Y component, which one is very important and to which our eyes are more sensitive, as you can see, the number of pixels remains unaltered. So, it has got 4800 blocks. So, after after block preparation, the Y component has got 4800 blocks and each block can be processed separately. On the other hand, the U and V blocks, they are averaged, I mean 4 pixels are averaged to generate 1 pixel, and giving you that U and V both are represented by 320 by 240 after averaging out. So, after averaging out we get to 320 by 240 So, this significantly reduces the size, and in turn the number of blocks to be processed is reduced to 1200 for each. So, 1200, 1200, 1200 for U and 1200 for V, and 4800 for 4800 for Y. So, altogether 7200 blocks are to be processed. Let us see what kind of processing is done for each, how each block is processed. Each block of 64 pixels, that is 8 by 8, goes through a transformation called discrete cosine transform. This discrete cosine transform is highly mathematical. We shall not discuss any mathematical equations. Rather, I shall give 3 examples to show how it helps to minimize the information, or how the numbers reduced. We have seen ultimately we have got a block where there are 8 into 8 64 numbers. Now, if as it is necessary to send 64 numbers, each of 8 bit. However, suppose there is a block where there is uniform intensity, there is no change. By using discrete Fourier transform, it is converted into a frame. As you can see here, we have got only one DC component, and all the AC component, which essentially represent changes with respect to this 0 point, and AC components are 0, because with respect to that there is no difference in any other pixel. So, essentially it has got one DC component and all DC components are 0. So, you can see these zeros can ultimately send in a very compact form, as we shall see later. Then let us consider the second case, where you have got 2 different tones, that means 2 different intensities, 1 and 2, and as you can see intensity level is represented by 20 20 20 20, and the other half is 50 50 50. So, after discrete cosine transform, as you can see, it has got one DC component and few AC components and a large number of 0 values. So, the number of zeros is significantly increased, and you have got very few AC components and a DC components. Now, if the intensity changes uniformly, as you can see here, say 20, 30, 40, 50, 60, 70, 80, 90, then also after discrete cosine transform, it generates numbers like 400, which is essentially average value with a multiplication factor, and other AC values like 46, 0 and so on. So, these are the AC components, and here also you see you have got large number of zeros. Of course, in real life picture you will not have a uniform tone, or just 2 tones, or a gradually increasing tone. It will be some variations. Of course, the number of AC components will be larger than this, but definitely it will have a large number of zeros. So, this is how discrete cosine transform is performed, and it produces essentially it helps to get a large number of zeros in different pixel points. Now, another step is performed, which is known as quantization, which further increases the number of zeros. As you have seen that this DC component is the most important component, and around that other components are important. However, the pixel components on this side are, that means this corner, are not really that much important. So, they are divided by different numbers, and then the fraction part is removed. For example, these 4 pixel values, I mean those values are divided by 1, then this row and this column, these values are divided by 2, then this row and this column values are divided by 4, and in this way the last row and last column is divided by 64, and as a consequence, for example, if this is the original discrete cosine transform coefficients, after performing quantization you can see the number of zeros has increased. For example, in this range we have more number of zeros compared to this one. So, this helps you to increase the number of zeros after quantization. And in fact, this the MPEG is lossy because of this quantization steps. The prior steps, that DCT and block preparation, they are not essentially lossy, but this is where some information loss takes place because of quantization. However, our eyes will not be able to detect the differences. After this, after we have got the blocks, each block is scanned in this zigzag fashion, this one, this one, this one, then this one, this one, this one, in this way. You may be asking, what is the purpose of this? The purpose is, if you scan in this manner, then the runs of zeros will be lesser than if you scan in this zigzag fashion. For example, if you scan in a horizontal manner, the number of zeros in consecutive locations will be 24 plus 7, that means 31. On the other hand, if you scan in this manner, zigzag manner, you can see from here all are zeros. So, you have got 38 zeros in a row, that is called runs of zeros. It essentially helps you to get more runs of zeros. Then these runs of zeros can be sent in a compact form as it is shown here. For example, this 26, here there are 26 zeros, and these 26 zeros can be sent by this part of the information. So, a block is now converted into fewer numbers, 2, 1, A, 0, 26, 3. So, you see initially we had 64 numbers, now it has got converted into fewer numbers, and that can be transmitted to the other end, and where the decoding can be done to get back the original signal. So, this is the basic concept behind the JPEG. Now, let us see what is performed by MPEG. MPEG 1 was the first standard to be finalized for video compression, for interactive video on CDs, and for digital audio broadcasting. And with the help of MPEG 1, a VCR quality video having 640 by 480 pixels with 24 frames per second, 25 frames per second and 24 bits per pixel gives you 368.64 megabits per second in uncompressed form. This is in uncompressed form. And after performing MPEG 1 compression, it produces 1.5 megabits per second. So, you see there is a tremendous compression ratio, significant reduction in the size, and which can be sent through many networks, and this 368.64 is very difficult to send through many networks, cannot be sent. And this MPEG 1 is likely to dominate the encoding of CD-ROM based movies, because it gives you quite good quality performance. And another advantage is this 1.5 megabits per second can be transmitted over twisted pair for modest distances. For example, it can be transmitted through ADSL network quite efficiently. So, by using ADSL, using twisted pair of network, it can be sent over a distance of 18,000 feet or roughly 5 kilometer. So, because of this compression, it is possible to send MPEG video through ADSL. MPEG has three components: audio, video and system. How the audio compression is done we have already discussed. So, audio signal is applied to the audio encoder, and which does the compression independent of the video compression, video encoder. So, video signal is applied to the video encoder and audio signal is applied to the audio encoder after the sampling. Now, a clock is used which operates at 90 kilohertz to provide the information of time in the form of time stamp. So, this time stamping is performed, and this time stamped audio and video signals are multiplexed to generate MPEG-1 output, which goes all the way, which is propagated all the way to the receiver. So, this time stamping helps you to do the synchronization of the audio and video signal. As we have seen, one of the important SS factor is lip synchronization. One of the important requirement is lip synchronization. So, to facilitate lip synchronization, this kind of time stamping is necessary, and this time stamping is also necessary for streaming, as we shall see in the next lecture. Let us see how MPEG video compression is performed. Encoding each frame separately with JPEG removes spatial redundancy. We have already seen how JPEG can be used to remove spatial redundancy, and this is used when, however, just JPEG encoded frames can be sent without further compression, and this can be done in situations where each frame is accessed separately randomly, such as when you are editing for video productions. And however, in such a case, after compression you will get 8 to 10 megabits per second compressed bandwidth, not very high compression. However, additional compression can be achieved by taking advantage of the fact that consecutive frames are often almost identical, that is temporal redundancy. For example, here two frames are shown here. This is frame 1 and let us say this is frame n. As you can see here, in this frame the background is identical. This house, this tree, these are all same, except the blocks in which this person is there and the blocks in which this person is here. So, in this region and this region, only in these two regions there are differences. So, if this frame is used to reconstruct this frame, only information of this block, in the block of this block and also of this block is sufficient to encode this frame, and also at the receiving end to regenerate this frame from this frame. So, this is the basic idea behind this MPEG. And to do that, MPEG output consists of 4 kinds of frames for motion compensation. Essentially, what you have to do, the difference between two frames are to be compensated, which is known as motion compensation. And this is done by sending 4 different types of frames. First one is I type of frame, and this I type of frames are which are essentially intra-code frames. These are self-contained JPEG encoded and which appears periodically. So, they are essentially JPEG encoded and contains all the information after JPEG encoding, and they can be decoded independently. On the other hand, the P type, the predictive frames, which are block by block, which uses the block by block difference with the preceding I or P frame. So, a P type of frame which is predictive frames cannot be decoded independently, which are not self-contained. So, preceding I and P frames will be required to encode P frames and also regenerate or decode the P frames. Another type of frames are there sent which are known as bidirectional frames. In bidirectional frames, differences with the preceding and also the following I and P frames are used as references. So, these are the 3 basic frames are used. However, this D type of frames, which are essentially block averages, which are essentially used for fast forward. So, not really used for compression. Now, let us see how I, P and B frames are used. Here, for example, this is the order in which different frames are to be displayed. This is a I frame. This 2, 3 and 4 are B frames. That means 2 depends on 1 as well as on 5. 3 depends on 1 as well as on 5. 4 also depends on 1 as well as on 5. On the other hand, 5 depends only on 1, predictive, the previous one, not the succeeding following one. 6 depends on 1 as well as 9. 7 depends on 1 as well as 9, 8 depends on 1 as well as 9. On the other hand, 9 depends on only on 1 and maybe on 5. Now, since because of this dependency, what is being done, the encoder does not send the frames in this order, the way they are to be displayed. What is being done? First 1 is sent, then 5 is sent, because as you can see 2, 3 and 4 will require the information of 1 as well as 5. So, it is necessary to receive the frame 5 before 2, 3 and 4 can be reconstructed at the receiving end. So, that is why 1 is sent, then the 5 is sent, then 2, 3, 4. Similarly, 9 is sent before 6, 7 and 8. So, you can see the display order and the coding order is different. So, the encoder generates the frame in this form, which is being received by the decoder, and the decoder, after doing the necessary processing, will again display in this order 1, 2, 3, 4 in a natural sequence. So, one observation is coding and display order can be different. Second is encoder encoder takes minutes or hours to do the encoding of data, but decoder has to be fast. So, it has been observed that encoder algorithm is quite complex. So, it may take minutes or hours for encoding purpose. However, at the receiving end, the decoder has to do on the fly processing and display the images. That is why the decoder has to be pretty fast. So, there is a difference in the complexity of encoding encoder and decoder. Now, let us consider the MPEG-2. Although MPEG-2 is similar to MPEG-1, it was developed for digital television, and of course, in this case D frames are not supported, because usually in television you do not really do fast forward or anything of that kind. So, D types of frames are not really required, and to have better quality, DCT is 10 by 8, 10 bit by 10 bit instead of 8 by 8 bit that is used in MPEG-1 to provide better quality. And it supports 4 different resolutions, two of them are shown here, HD TV and TV, another 2 are there, and it supports 5 different profiles for different applications. So, you can see this MPEG-2 provides a different options. It is somewhat like shopping list. You choose this resolution or for a particular profile. So, you have got choices you can make, and accordingly for depending on your application. And MPEG-2 has a more general way of multiplexing. Here each streams are packetized with timestamps, as is done in case of MPEG-1, and the output of each packetizer is a packetized elementary system having 32 header fields. So, each packetizer produces a packetized elementary system which has got 30 header fields. That 30 header fields are essentially gives it time stamping, error detection, and various other fields are there which are used. Then these are multiplexed. One is PS multiplexer, which is essentially program multiplexer, another is transform multiplexer. This program multiplexer is essentially variable length packets and common time base. Because of that, as we have seen, after compression it can generate variable rate data, and that is why this PS is variable length packets. However, a common time base is used. On the other hand, this transport sequence, which is a fixed length packets with no common time base. So, these two are sent after the compression. Coming to the MPEG-4, MPEG-4 video compression project started as a standard for very low bit rates. So, for use in portable applications like video phones. So, to support very low bit rates, this MPEG-4 is being used, and this standard includes much more than just data compression. We have seen in MPEG-1 and MPEG-2 essentially the techniques are concerned with compression, but apart from compression, as you can see, MPEG-4 has got many important functionalities, and some of the important functionalities are mentioned here: content based multimedia access tools, content based manipulation and bitstream editing, hybrid natural and synthetic data coding, improved temporal random access, improved coding efficiency, coding of multiple concurrent data streams, robustness in error prone environment, and content based scalability. So, main feature, as you can see, it has got many facilities for content based processing. Nowadays, those who are watching say relay of cricket matches, you must have noticed sometimes whenever a batsman is out or a bowler receives a catch, that part can be replayed very quickly, and that is precisely because of this content based multimedia access tools. Or a commentator when he is commentating about some catch or misfielding or something like that, these situations can be very easily identified and accessed with the help of this kind of processing capability, and MPEG-4 allows that. Moreover, it allows some kind of data stream. So, multilingual transmission is also allowed with the help of MPEG-4. Now, let us focus on the last standard, that is your H.261. This H.261 was developed as a standard for digital telephony for ISDN services. As you have seen, in case of ISDN services, the rates are multiples of 64 kilobits per second, and that is why after compression it is essentially necessary to transmit at a rate lower than 64 kilobits or some multiple of it. So, H.261 limits the images to just two sizes. One is known as common intermediate format CIF or quarter intermediate format QCIF. So, using CIF, the frame size is 352 by 288, and each pixel is represented by 8 bit, and there are 15 frames per second. So, that gives you 24.33 megabits per second without compression, and by using H.261 compression you get 112 kilobits per second. And in case of QCIF, still smaller frame size is used, and the number of frames per second is also reduced from 15 to 10. Of course, the number of bits used for each pixel is 8, and the uncompressed signal has got 4.0 megabits per second, and after compression by using MPEG-4 you can also use H.261, it gives you less than 64 kilobits per second. So, you see this is primarily used for transmission through ISDN network. And another requirement of H.261 is the both encoder and decoder have to be fast because both operate in real time. So, in case of MPEG-1 or MPEG-2 or MPEG-4, we have seen that encoder can be very slow because it is very complex. On the other hand, decoder has to be fast, but in case of H.261, both encoder and decoder has to be very fast, because it is used for interactive video transmission, that is your, for example, video conferencing and other thing. And like MPEG, the compressed stream is organized in layers and macro blocks, and like MPEG, it uses 8 by 8 DCT and zigzag order, as you have seen, for the purpose of compression, and motion compensation is used when pictures are predicted from other pictures and motion vectors are coded as differences. So, and this part is very similar to MPEG. The way the motion compensation is done in MPEG, it is done in the similar manner in H.261. So, we have discussed different audio and video compression techniques in this lecture, and let us see the review questions. First question is, why do you need data compression? Second question is, distinguish between frequency masking and temporal masking. Third question is, compare the importance of luminance compared to chrominance in the context of compression, obviously in the context of video compression. Fourth is, distinguish between spatial and temporal redundancy. Fifth question is, what is motion compensation? Now it is time to give you the answers of questions of lecture number 36. First question was, what do you mean by multimedia? As we know, multimedia stands for more than one media. So, by definition, multimedia means more than one media such as text, graphics, audio, video and animation. For example, while delivering this lecture, I have used text and also used graphics and animation. So, you can say I have used multimedia presentations, and also audio video is being used. However, it is commonly referred to two or more continuous media such as audio and video played during some well defined time interval using user interaction. So, commonly this is how the multimedia is defined, although multimedia usually by meaning multimedia refers to more than one media such as text, graphics, audio, video and animation. Second question was, what is SAS, synchronization accuracy specification, and what role it plays in multimedia communication? As we have seen, for the multimedia signals require bandwidth as well as SAS factors to specify the goodness of for transmission, and particularly the SAS factors comprises four parameters like delay, delay jitter, delay skew and error rate, as we have already discussed in detail, and they specify the goodness of synchronization of multimedia stream in addition to the bandwidth which is required. It ensures occurrence of events at the same time such as lip synchronization, and this synchronization accuracy specification ensures that all the multimedia signals take place in precise time instants in a synchronized manner. So, that is the role of SAS factors. Third question was, explain the function of NPPs in multimedia communication. So, for multimedia transmission, the requirement is specified by SAS factors and bandwidth. On the other hand, the network parameters or network performance is specified in terms of network performance parameters, and these two are to be compared, the network performance parameter and SAS factors as well as bandwidth requirement of an application. By comparing them, one can determine whether or not the network is capable of carrying multimedia traffic. So, this network performance parameter is very essential to decide whether a network is suitable for multimedia communication or not. So, that is why this is very important. Fourth question was, distinguish between BRI and PRI of ISDN. We have seen the ISDN uses two interfaces, two important interfaces. One is known as basic rate interface BRI, that specifies a digital pipe comprising two 64 kilobits per second B channels and one 16 kilobits per channel D second. So, this is of lower bandwidth and it is designed to meet the requirements of residential as well as small offices. On the other hand, the primary rate interface PRI specifies a digital pipe with 23 B channels, each of 64 kilobits per second, and one D channel that also is of 64 kilobits per second. So, obviously with the help of this you can achieve much higher bandwidth and which can support multimedia transmission at video quality, and obviously a BRI interface cannot support multimedia transmission at video quality. And of course, whenever you have got BRI interface, apart from video quality transmission, multimedia transmission, you can use it of various other applications such as data communication. Last question was, explain the role of RTP and RCTP. RTP is a transport layer protocol on top of UDP to support real time traffic. As we have seen, UDP is a connectionless unreliable protocol, so it cannot really support multimedia communication. So, to facilitate that, UDP should use RTP, that means UDP should be used in conjunction with RTP to support real time traffic. So, RTP provides end-to-end transport services to real time audio, video and simulation data. Of course, for control information you require another protocol, that is your RCTP, that allows communication of control information. So, with this we come to the end of today's lecture, and we have discussed how audio and video compression can be performed. In the next lecture we shall discuss the different applications possible because of this compression. Thank you.